Hello students, in this session we'll learn concept of Cauchy sequence in set of real numbers. We are well familiar with convergent sequence. A real sequence Sn is said to be convergent if for very large n, Sns are very close to particular real number L, then we say that sequence Sn converges to a real number L. On the other hand, a sequence Sn is said to be Cauchy sequence if for very large n, after very large n, the terms of that sequence Sn and Sm are very close to each other. Very close to each other. So, we'll state this in mathematical expression as follows. So, what is a Cauchy sequence? A real sequence Sn n equal to 1 to infinity is Cauchy sequence if for given epsilon greater than 0, there exists positive integer n naught such that mod of xn minus xm is less than epsilon for any mn greater equal n naught. Means after n naught, all xn and xm's are very close to each other. Epsilon is arbitrary, means epsilon is even though very small, it is very near to 0. Distance between x and xm is very small, means they are close to each other. In that case, that terms are closure. Example, so that say if I take n upon n plus 1 or say n plus 1 upon n is Cauchy sequence. So here Sn is equal to, for this sequence, what is your Sn? N plus 1 upon n for every n. Now mod of Sn minus Sm, this is nothing but mod of n plus 1 upon n minus, I can write this as 1 plus 1 upon n. So for all n, so Sn minus Sm is written as 1 plus 1 upon n minus 1 plus 1 upon m. This 1 get cancelled, will get mod of 1 by n minus 1 by m. By triangle inequality, this is less equal. 1 by n plus 1 by m. And then this is less equal again 2 by n for, and this is again less equal 2 by n naught for any m greater equal n greater equal n naught. This is equivalent to 1 upon m is less than equal to 1 by n less equal 1 by n naught. Okay. So we'll get this 1. Now for epsilon greater than 0, 2 by n naught is less than epsilon if and only if n naught is greater than 2 by epsilon. So from 1 and 2, for given epsilon greater than 0, there exists positive integer n naught greater than 2 by epsilon by Archimedean property such that mod of Sn minus Sm is less than epsilon for any m greater equal n greater than equal to n naught. And therefore, your Sn is equal to n plus 1 upon n equal to 1 to infinity is Cauchy sequence. Later on, we are going to prove result that every convergent sequence is always Cauchy sequence. In fact, we immediately will prove that result. So, which examples we have proved to be convergent sequence by epsilon n naught definition? You can also prove that are the examples of Cauchy sequences. Okay. So now we'll prove the result that every Cauchy sequence is convergent. Okay. Theorem. Every Cauchy sequence, every convergent sequence is Cauchy sequence. In set of real number, we are going to prove that every Cauchy sequence is also convergent. But in general, in any metric space, convergent sequence is always Cauchy, but Cauchy sequence need not be convergent. Okay. In set of real number, with respect to usual metric, convergent sequence is equivalent to Cauchy sequence. Means Cauchy sequence is Cauchy pan only if it is convergent. Okay. But in general, result is not true. So, take some convergence sequence. Let Sn n equal to 1 to infinity be convergent sequence such that limit n tends to infinity of Sn is equal to L. Okay. Our aim is to show that. Okay. Claim Sn is Cauchy sequence. Means for given epsilon greater than 0, we have to find some positive integer n naught such that mod Sn minus Sm is less than epsilon. And we have to relate that mod Sn minus Sm with epsilon via limit of sequence, because we have to use convergence of that sequence somewhere. Is it right? So we have to insert L in mod Sn minus Sm. Okay. So for this, mod Sn minus Sm is same as mod of Sn minus L plus L minus Sm. But by triangle inequality, this is less equal mod Sn minus L plus mod of L minus Sm, which is same as mod of Sm minus L by triangle inequality. Okay. Triangle inequality. We'll get this. Okay. Now from 1 for given epsilon greater than 0, there exists positive integer n naught such that mod of Sn minus L is less than epsilon by 2 for any n greater equal n naught. Why I am taking here less than epsilon by 2? Because I want this to be less than epsilon by 2 plus epsilon by 2, which is equal to epsilon. Okay. So from 2 and 3, mod of Sn minus Sm is less than epsilon by 2 plus epsilon by 2 is equal to epsilon for any mn greater equal n naught. Thus, for given epsilon greater than 0, for any epsilon greater than 0, there exists positive integer n naught such that mod Sn minus Sm is less than epsilon for any mn greater equal n naught, and therefore Sn is Cauchy sequence. Hence proved. Thus the result is proved. So we proved that every convergent sequence of real numbers is Cauchy sequence. I told you that every Cauchy sequence is convergent, convergent sequence is bounded, means Cauchy sequence must be bounded sequence. So we'll prove result that every Cauchy sequence is bounded now. Okay. Next theorem. Every Cauchy sequence is bounded. So let Sn be Cauchy sequence of real numbers. So for given epsilon greater than 0, there is always some positive integer n not satisfying condition mod Sn minus Sm less than epsilon. So as here we have to show that it is bounded, so we'll take that epsilon to be some fixed real number. So therefore for epsilon is equal to 1 greater than 0, there exists positive integer n naught such that mod of Sn minus Sn naught, Sn minus Sm less than epsilon for any mn greater or equal n naught. In particular, if I replace m by n naught, therefore mod Sn minus Sn naught is also less than 1 for any n greater or equal n naught. For any n greater or equal n naught. Is it clear? Now, this is a 1. Now, mod of Sn is equal to mod of Sn minus Sn naught plus Sn naught. By triangle inequality, this is less equal mod Sn minus Sn naught plus mod of Sn naught. Okay. By triangle inequality. Triangle inequality, and this is less than 1 plus mod Sn naught for any n greater or equal n naught. Okay. This is 2 and by 1. By 1. Okay. Now take m is equal to maximum of mod S1, mod S2 and so on mod Sn naught and 1 plus mod Sn naught. Right? Then from 2 and 3, after n greater or equal n naught, all Sn have modulus value less than 1 plus mod Sn naught, and remaining terms are less equal maximum of this, and therefore mod Sn must be less equal m for every n greater for every n. Implies Sn is convergent sequence, is bounded sequence. Every bounded sequence, every Cauchy sequence is bounded. Every Cauchy sequence is bounded. So, converse is not true. Note, converse is not true. Is not true. For example, minus 1 raised to n is bounded sequence such that mod of Sn minus Sn minus 1. If I take this to be Sn, this must be whatever this, minus 1 raised to n minus 1 raised to n minus 1, which is 2, for every n, not less than epsilon, for epsilon 0 less than epsilon less than 2. Okay. Implies minus 1 raised to n is not Cauchy, is not Cauchy sequence. So this is bounded because mod of Sn is 1 less equal 1. Okay. So this is the example of bounded sequence which is not Cauchy sequence. I am again saying that every Cauchy sequence is convergent. Convergent sequence is Cauchy. So if you get the example of bounded sequence which are not convergent, that must not be Cauchy. Okay. And now we'll prove the important result that every Cauchy sequence is convergent. Okay. Next theorem. Every Cauchy sequence of real numbers is convergent. So let Sn n equal to 1 to infinity be Cauchy sequence, real Cauchy sequence or Cauchy sequence of real numbers. Our aim is to show that it is convergent. Claim Sn is convergent. By sufficient condition, it is sufficient to show by sufficient condition. It is sufficient to show lim sup of Sn is equal to lim inf of Sn. Okay. Again, now Sn is Cauchy sequence and hence bounded sequence. Therefore, lim sup of Sn and lim inf of Sn exist. Okay, this exists. Now we have given it is Cauchy sequence. Okay. Since Sn is Cauchy sequence, Sn is Cauchy, therefore for given epsilon greater than 0, there exists positive integer n naught such that mod of Sn minus Sm is less than epsilon by 2 for any mn greater or equal n naught. In particular, mod of Sn minus Sn naught is also less than epsilon by 2 for every n greater or equal n naught. This is equivalent to Sn naught minus epsilon by 2 is less than Sn is less than Sn naught plus epsilon by 2 n greater or equal n naught. All Sn lies between Sn naught minus epsilon by 2, Sn naught plus epsilon by 2. Okay. This implies Sn naught plus epsilon by 2 is upper bound for Sn, Sm plus 1 and so on for any n greater or equal n naught, and Sn naught minus epsilon by 2 is lower bound, and Sn naught minus epsilon by 2 is lower bound for Sn plus 1 and so on for every n greater equal n naught. What this implies is where epsilon is arbitrary. Epsilon greater than 0 is arbitrary. Epsilon tending to 0. The result is true. Implies Sn naught minus epsilon by 2. Therefore, Sn naught minus epsilon by 2 is less equal greatest lower bound of Sn plus 1 and so on is less equal least upper bound of set Sn plus 1 less than Sn naught plus epsilon by 2 for any n greater equal n naught. For any n greater equal n naught. Okay. This implies Sn naught minus greatest lower bound of Sn plus 1 and so on is less equal minus Sn naught plus epsilon by 2 and least upper bound of Sn plus 1 and so on is less equal Sn naught plus epsilon by 2 for any n greater equal n naught. Adding these two inequalities, we get if I add these two, we'll get least upper bound of Sn plus 1 and so on minus greatest lower bound of Sn plus 1 and so on is less than equal to epsilon for any n greater equal n naught. And therefore, least upper bound of the set Sn plus 1 and so on is less equal greatest lower bound of Sn plus 1 plus epsilon for any n greater equal n naught, which implies least upper bound of set Sn plus 1 and so on is less equal greatest lower bound of Sn plus 1 and so on for any n greater equal n naught, since epsilon greater than 0 is arbitrary. Is it right? So this is A now. Okay. What this implies? Lim sup of Sn is less equal lim inf of Sn. We also know for any sequence Sn, whatever it may be bounded or unbounded, okay, lim inf is always less equal lim sup. We know for any sequence Sn, lim inf of Sn, we have proved this result, is less equal lim sup of Sn. From A and B, equality hold. From A and B, lim sup of Sn is equal to lim inf of Sn. Lim inf of Sn, and therefore limit of Sn exist. and therefore Sn is convergent is equal to limit of Sn. Thus every Cauchy sequence is convergent. Every Cauchy sequence is convergent. We can prove this result alternatively also. Alternate proof. Since Sn is Cauchy sequence, therefore Sn is bounded sequence. Every Cauchy sequence is bounded, and therefore Sn has a convergent subsequence. Say Snk. Suppose limit Snk is equal to k tends to infinity is equal to L. Then for given epsilon greater than 0, there exists n1 such that mod of Snk minus L is less than epsilon by 2 for any nk greater equal n1. 1. Okay. Now Snk is Cauchy sequence. Since Sn is Cauchy sequence, therefore for epsilon greater than 0, fix epsilon greater than 0, there exists positive integer n2 such that mod Sn minus Sm is less than epsilon by 2 for any mn greater equal n2. Okay. Choose n0 is equal to maximum of n1 n2. Then mod Snk minus L is less than epsilon by 2, mod Sn minus Sm less than epsilon by 2 for any nk mn greater equal n0. Okay, this is 3 from 1 and 2. From 1 and 2. Now mod of Sn minus L, I can write this as mod Sn minus Snk plus Snk minus L. This is less equal mod Sn minus Snk plus mod of Snk minus L. This is less than epsilon by 2 plus epsilon by 2 is equal to epsilon for any n nk greater equal n0. N nk greater equal n0. From 3. From 3. Thus for given epsilon greater than 0, there exists positive integer n0 such that mod of Sn minus L less than epsilon for any n greater equal n0, and therefore limit of Sn is equal to L. Therefore Sn is convergent sequence. Thus every Cauchy sequence is convergent. Okay. Thus every Cauchy sequence is convergent. So we proved the real sequence is Cauchy if and only if it is convergent sequence. So with this discussion Today we'll stop our session here. Thanks for listening lecture carefully. Bye bye.